All right. So my name is Leif for the people that haven't met me yet or I haven't talked to on Facebook yet. And today I'm going to be presenting principal component analysis. And before I start, I want to say thank you to Professor Christina because she allowed me to take some might find boring, I find really interesting topic and get to apply it to machine learning, data, the fun stuff, the stuff I find fun, and it would make it even more fun for you guys to learn um, which I think is pretty cool. So there's that. So the goal of this presentation is that at the end of it, everyone here could describe what PCA is at some level to any friend, regardless of what they're studying. Understand the math behind PCA, eigenvectors, eigenvalues, covariance, matrix, all that. And also learn something new about machine learning, because we're going to do a little bit of machine learning. For some of you who have never heard of what machine learning is, you'll know what it is by the end of this presentation. The agenda for today is I'm going to teach you everything you need to know about PCA, what it is and how it works. There's not going to be any stocks in that just because I think the fundamentals have to be talked about before we get into the data. Then we're going to talk about the goal, what we're trying to do with the stocks data, because we have to have a goal that we're working towards if we're looking at data and trying to solve a problem. We're going to explore the data, apply PCA, which is going to be the big chunk of this presentation. We're going to do a small introduction to machine learning, train and test our machine learning model, and then at the end we'll have some Q&A time. Before I continue, I just want to talk about the environment I'm presenting. This is obviously not PowerPoint. Anything that looks like this is code. You don't need to worry about that. If there is code I want you to understand, I will explain it. But what I'm coding in, it's nice because it allows me to write normal text like this and code at the same time. It just makes it easier to talk about stuff. So don't worry about anything that doesn't make sense. To get started, we're going to talk about everything we need to know about PCA. So the way I want to explain it is through examples, because I think that's the way I understood it best. So PCA, principal component analysis, is basically a dimensionality reduction method. So say we're working with 4 or more dimensions, PCA helps us to reduce the dimensions to 2 or 3 dimensions that we're able to plot, observe, kind of visualize, makes it easier for us to read data. Here's the example. I'm just going to jump right into the example. Say we have a table and we looked at the counts of genes in different mice. So we have mouse 1, mouse 2, mouse 3, and mouse 4. And we have gene 1, gene 2, gene 3, and gene 4. Just for your information, throughout the presentation, I'm going to use the words independent variables, column, dimensions, and features all interchangeably. They all mean the same thing. So we have 4 features here, 4 columns, 4 dimensions, all same thing. So say we're the scientist, we get this piece of data and we want to kind of make sense of the data. We decide to plot gene 1 versus gene 2 to see how it looks like. And we see that mouse 1 and mouse 2 are similar to each other, and mouse 3 and mouse 4 are also similar to each other. Great. We want to include more of the data because we want to try to get all the data into the plot. So we decide to include gene 3. So it becomes a 3-dimensional graph, like on the right over here. We plotted gene 1, gene 2, and gene 3, and we could still see that mouse 1, mouse 2 are similar to each other. Mouse 3 and mouse 4 are also similar to each other. Great. We're almost there to get all our data in there. Now we have to plot gene 4 in there as well. But the problem is with gene 4, even if it is possible, it's very hard for us to visualize and make sense of the data if we're trying to plot anything more than 3-dimensional. And this is where PCA comes from when it comes to data analysis and working with data and applying PCA. PCA takes those 4 dimensions, gene 1, gene 2, gene 3, and gene 4 in our table and is able to reduce them to 2 axes, 2-dimensional, principal component 1, principal component 2, and it helps us plot the data, and we could still see the clustering of similar instances. So we still see mouse 1 and mouse 2 together, mouse 3 and mouse 4 still together. So this, as you can see, could be very useful for people that are working with a large number of dimensions and they're trying to better understand the data or trying to reduce the amount of computational time if they're doing any machine learning work. They use PCA to reduce the dimensions, reduce the amount of features, and be able to work with it easier. So how does it take this 4-dimensional table or data and reduce it to only 2-dimensional, principal component 1, principal component 2? It's actually pretty straightforward. So I'll give you the word definition of how it does it, then we'll go into the example again. So basically, what PCA does is the first principal component, our new x-axis here, will capture most variation in the data. Principal component 2 captures the second most variation in the data, and so on and so on. It does this for the n dimensions that we have. So in the table for the mice, we have 4 dimensions, gene 1, 2, 3, and 4. So PCA will find the principal component for each dimension. And then it is up to us if we want to say we want to reduce it to 2 dimensions. It'll take the first 2 dimensions that cover most of the variation of the data. I know that's kind of hard to wrap our head around. This is why we have the example, and we'll go step by step through it, how it works. So let's just start with the gene 1 versus gene 2, very easy 2 dimensions. We have our data, same as the one in the last page. The first thing we have to do to calculate PCA, whether it's machine learning or you're doing it by hand with equations, is we have to first standardize our data. And that just essentially means that we need the mean to be at the origin. The reason why we do this, just a quick explanation. For right now, our gene 1 goes from 0 to about 10, and gene 2 goes from 0 to about 6. But say our gene 1 went from 0, it ranges from 0 to 50,000, and our gene 2 only went from 0 to 6. Then PCA will automatically favor gene 1 because the variance in gene 1, the range of the values can be, is just much larger than gene 2, which is not necessarily as accurate. So we standardize our data. That's the goal. The first step is we standardize the data. We have the mean at the origin. And over here, before we worry what's on the right side, I want us to pay attention to this little plot over here. I drew a blue line that captures the variance from the left to the right of the data, and then the pink line captures it from the bottom to the top. So what PCA 1, since we're trying to find our principal component 1 first, principal component 1 has to capture the most variation in the data. So the blue line is clearly much bigger than the pink line. So we're going to focus on the blue line to become our PC1, our principal component 1. This blue line is actually the line of best fit for our data. So we want to make sure this blue line best represents the relationship in our data. And there's really 2 ways to do this. And before I get into the 2 ways, I just want to get rid of some of the data and focus more on the first quad just to make it easier to visualize. So we have our data point right there. We have our line of best fit. If we project that point onto the line of best fit, we get a right angle triangle. The distance from the origin to the projected point onto the line of best fit, that little X with the green color, that's our distance, that's D. From the point to its projected self onto the line of best fit, we're gonna call that A. And then from the origin to the actual point, that's going to be H. So the 2 ways we could find the line of best fit is, 1, we can minimize the distance A. So from the point to the actual line of best fit, we want to make sure the distance is as small as possible. That's one way to do it. The second way, which is the way that PCA does it, principal component analysis does it, is we want to maximize the distance from the origin to the projected point onto the line of best fit, so D. We want to make sure that's as big as possible. And just again, to illustrate the point a little bit better, imagine our blue line was like this. Can you guys see my cursor? Can you guys see? Okay, great. So imagine the blue line was like this, right? And the point is still in the same spot. If we project that point onto that line, the distance from here to here would be a lot smaller. And it's clear that a line like this does not fit as good as this blue line that we have already. That's what we're trying to maximize, that distance. The bigger it is, the better the line fits the data. So I just added the rest of the points that I removed earlier. I put back mouse 1, mouse 3, and mouse 4. I drew their projections onto the line of best fit. I only labeled the distance for mouse 1 just to emphasize the idea that's what we're aiming to maximize. And what PCA does is that it's trying to find the max of sum of squared distances. So it takes the distance, squares it, and then sums them all up for each mice that we have in our data. So we'll do it for mouse 2, mouse 3, and mouse 4. And the reason why we square the distance is really, if we have a negative distance, which I didn't really come across that. If there is a negative distance, it gets rid of any negatives that we have in our data. So it squares it up, adds them all together, and PCA is trying to maximize this because the bigger it is, the better the line fits the data. So now we have the line of best fit that covers the most variation in our data. That becomes our principal component 1. I drew an orange vector. That vector is a unit vector. It's on the principal component 1 on our line of best fit. That unit vector is called our eigenvector for principal component 1. This is where the math comes in. The sum of squared distances that we calculated earlier to find the line of best fit is now our eigenvalue for principal component 1. And the square root of the eigenvalue is called the singular value. I'm not going to talk much about singular value. I just put it in there because it was just part of the notes that I was reading in the different literatures that we're talking about PCA. So now we have our principal component 1. We want to get our principal component 2 because again, we started with gene 1 and gene 2. And principal component 2 is really easy. All it is just an orthogonal line to principal component 1, and it goes through the origin. Just like a normal XY graph, Y is always orthogonal to X, and it goes through the origin. And then all we have to do is just rotate PC1 and PC2, and we get our new graph. It's just simple as that. I tried to use the easiest example I could think of just to better illustrate my, my point on how it works. A little bit behind the math on how to compute the PCA. So the first step is, again, the standardization. The second step is we have to find the covariance matrix. So the covariance is just really the relationship between two variables. And what we want to do is we want to calculate the covariance between each variable that we have in our data. So here I have variable X, variable Y, variable Z, variable X, variable Y, variable Z, and we calculate the covariance between each one, and we end up with a matrix. This matrix is what we use to calculate the eigenvectors and the eigenvalues that would help us decide what principal components, where they are, and which ones we select. Because the eigenvalues, since they present the sum of squared distances, we select the largest eigenvalue, which is, and the respective eigenvector will be our principal component 1. And then so on and so on and so on. And for the n dimensions that we're working with. So PCA is really good. There's a lot of reasons why people use it. The 3 reasons that most popped up when I Googled the benefits of PCA is one is dimensionality reduction. That's obvious. It increases performance, but I want you to keep in mind when I say increases performance, it increases the speed, not necessarily the accuracy when it comes to machine learning or working with data. And it helps us visualize higher dimensions, just like what we did just now. I don't know if anyone has any questions about what I just said, but if you do, just send it in the chat. I don't mind stopping and answering it. Okay, so now we could actually get into the stocks. So I like to make it a little bit fun to give myself a little scenario and work with it. So say a hedge fund firm decided to hire us and they told us to look over some stocks. They sent us like a database of stocks with some attributes about the stocks, and they said find and identify the stocks that behave the same, and then use a machine learning model to predict some of the prices, to try to predict the prices of the stocks. So I would go through all the code of the data, but that will just take us forever. So I'm just gonna show you the final data that we have. I'm just gonna zoom out a little bit, Professor Christina, if you don't mind, because it shows all the columns together. Okay, great. So here's our table, what we're working with. Just to quickly explain it, we have the symbol. This is the stock, okay? Each stock has its own symbol for the company name. So we have the stock, we have the last price, the price of the stock, the change in that day, in dollar percentage, 52-week high, 52-week low, the volumes, the sector the company's in, the 3-month change, past 6 months, past year, past 3 years, 5 years, and 10 years. It's pretty straightforward data. We have, I believe, 293 in total stocks. It says 292 because it starts counting at 0. I guess it's just a CS thing or what data thing. I don't know why it does that, but it's 293 stocks that we're working with. And now we could just dive into it since we have a goal that we're trying to work towards. So this is just me cleaning up the data, making sure that it's clean. There's no missing values. They're actually numbers and not objects, stuff like that for the code to actually read it. We don't have to worry about that. So we're going to split our data. That's the first thing we're going to do. The easiest way to explain why we split our data, since it's not that important, I don't want to take up too much time on it, is say you have a math test tomorrow and your professor tells you to study 2 questions, 5 plus 5 and 2 plus 2. Then you show up to the test tomorrow and the questions are 5 plus 5, 2 plus 2. It doesn't make sense to be tested on the same things you just practiced. So that's why we split our data into 2 sets, and we train our model using the training one, and then we test it using the test set because they're different instances, different rows, because it doesn't make sense to test it on what we just trained it on. Don't stress too much about that. Just know we split our data into 2. And now here we standardize our data. Code is awesome for this reason. I don't really have to do too much computation. I just have to figure out exactly what I need to put in code for it to standardize it. But here's a step that we did to standardize the data before we could apply any PCA. Cool. I hope everyone's following so far. So now we're applying PCA. And I applied it in 2 different ways because I think the first way I applied it just makes it a lot easier for us to observe what's going on. Okay, so let's just be clear. Here's our data. These are our features, our columns, our dimensions. So just like how in the earlier example, we had gene 1, gene 2, gene 3, gene 4. For our stocks, these are the dimensions. We have the change, the 52-week high, low, volume, and the changes in the past. Those are the, we could assume those are the behavior of each stock. So 12 dimensions that we're working with, that we're starting off with. So we're gonna apply PCA. Again, don't worry about the code. So right here, this line that I'm highlighting, I'm just creating the PCA function and I'm telling it that we wanna reduce the dimensions from 12 to 2. This is why I have n components to 2. We want 2 principal components. And after applying the PCA function to our data, we end up with this value. For each stock, we have 2 coordinates. We have PC1 for principal component 1 and principal component 2, PC2. So keep in mind, we went from 12 dimensions for each stock to just 2 principal component 1 and principal component 2. I graphed it out and we could automatically see that most of the stocks are behaving somewhat similar. They're clustered together in this right bottom corner. Now, you'll see later on when I explain this graph a little bit more that this is not very accurate, but you kind of get the idea that what PCA does is that it kind of groups and shows small clusters of the data after it's applied to a set of data. So let me just explain what you see, and I'm gonna tie it back to that math steps that I did earlier on. So right now we're working with 234 different stocks. It's less than 293 because remember we split the data. We started off with 12 dimensions, the change in dollar percentage, the volumes, the 52-week high, and so on. And we told that we want our PCA function to reduce it to 2 dimensions. Here's our covariance matrix. It's 12 by 12, and we expect it to be 12 by 12 because we started off with 12 dimensions, 12 different variables. We calculate the covariance for each pair in the dimensions, right? So we have dimension 1, 2, 3, blah, blah, to 12, 1, 2, 3 to 12, the covariance of each one. Here are the eigenvectors. So here's eigenvector 1. This is for principal component 1. Because again, if you recall when we said, where does our principal component land on? It's the eigenvector, the line that best fits the most variation in our data. And here's eigenvector 2. So we have 2 because we have reduced to 2 dimensions. Here they are, principal component 1, principal component 2. Here's the one thing that kind of, for me, it just tied everything together when I was researching PCA. Our eigenvalues, it's 2.95 and 2.10. They're in descending order. And that makes perfect sense since we know that our principal component 1 has to cover the most variation in data. That means it's gonna have to have the largest sum of squared differences. So the eigenvalue is gonna be larger for PC1 than PC2. Also for the percentage of variance explained by each component, it's 24% for the first for the first principal component, and 17% for the second principal component. Again, it's in descending order because we expected it to behave this way. Principal component 1 is supposed to capture the most variation in the data. So hopefully that makes sense. Again, if there's any questions, please put it in the chat.
I'm asking you to zoom in again because I have to.
Oh,
yeah.
That's fine. Yeah, sorry. Okay, come on. Oh, I'm pressing down Control, not Command. Is that good enough, or do you want one more? You got? Okay, great.
One more.
Oh, one more. There we go. Okay. So don't, oh, it's still loading. There we go. It just changed a little format. Nothing changed, don't worry. So don't be overwhelmed by the decimals and the large matrix or anything like that. This is why I printed out what each thing is doing. The covariance matrix, if you take this matrix and you plug it into Symbol Lab and you're asking it to find the eigenvectors or the eigenvalues, these are the eigenvectors that you will get and the eigenvalues. This is stuff that we know how to do, so it's nothing really new. It's just the order of steps that we're doing it. Okay. So now we're going to take our data and actually apply it to our original data. And now, since over here, when we reduced it to 2 dimensions, it only covered 42% when we reduced it from 12 dimensions to 2 dimensions. There's going to be obviously some loss of information. So we're trying to capture as much variance as we can, but since we kind of reduced it to little dimensions, we weren't able to capture as much variance as we would like to. We were only allowed to get 42% using 2 principal components, which is really bad. In the real world, losing more than 50% of your information is not good. So from the literature that I've read that Christina was kind enough to send me and the YouTubes that I was watching, they were all saying we want to at least have 85% of variance after applying PCA. But I'm just going to apply with 80% variance just because it worked better for this example and we don't have a lot of data to begin with. So here we go. The same PCA function, but instead of reducing it to 2 dimensions, I'm just going to say get as many dimensions as you need to get at least 80% of variance of our data. So we're not losing too much information. And that just happens to be 6 principal components. So we went from 12 dimensions to 6 dimensions for each stock. Same idea, just like the last one, but the last one is 2 principal components. Another thing I want us to kind of pay attention, PC1 and PC2 are the exact same ones from when we reduced it to 2 dimensions. They're the exact same values. And the reason why is because we applied it to the same data. And as we know, after it finds a covariance matrix and it does the eigenvectors, finds the eigenvectors for each dimension, for each 12 dimensions, and we select the amount of dimensions we want to reduce to, and it's already in order of the principal components that capture the most variance, we're going to have the first 2 principal components the same. The first 2 eigenvectors the same because it's the same data. It's just now we're selecting more principal components. So I'm going to graph it. This also I'm going to zoom out again, Professor, if you don't mind, just because it's kind of annoying how big my screen is. Okay, great. Might seem a little bit overwhelming, but it's more extra than it really needs to be. Since we have 6 principal components, it's kind of hard to just plot a 6-dimensional graph and read it. So this is a scatterplot matrix for anyone who has never seen one before. We have PC1 right here, 2, 3, 4, 5 to 6. And the same thing on this side. We have PC1, 2, 3, 4 up to 6. And it plots it against each other at the intersection. So this is PC1 against PC6, 2 against 6, and so on. One thing we should notice is that the diagonal is just a linear line. And the reason why is because the principal components are plotted against each other. That means it's just the same variable. It's 1-dimensional. So PC6 here is plotted against its own PC6. So it's going to end up being a line, 1D. and same thing across the diagonal. Also, another thing to notice, the upper right side of the matrix is the same thing as the bottom left. It's just rotated, because if we look at this right here where my cursor decides to get a little bit big, we have PC6 plotted against PC5. And this graph right here is just PC5 plotted against PC6. It's the same thing, it's just rotated. So don't even stress the right side of the right half of the matrix. But we can look and observe this bottom half. And right away, we could still see the same behavior with the clustering. We see most of the stocks fall into the same cluster, no matter which scatter plot we want to look at. Right here, and right here. We'll look into more of this graph after we do the same stats that we did previously, so we could actually see more details on how it behaves. Same thing, 234 stocks that we're looking at. We started with 12 dimensions and we reduced it to 6. Here's the covariance matrix, which is the same matrix as the one before. Remember, the matrix doesn't change. We applied it to the same data. Here are the eigenvectors. There's 6 of them because we have 6 principal components. And the first 2 are the same ones as the previous attempt we put PCA, right? Here's the eigenvalues and the variance covered by each principal component. And what we said before about it being in descending order is still applies. This is only gonna get less and less and less. Same thing with the variance captured by each principal component. Because as I said like 20 times by now, the first principal component captures the most variation in the data. Second one captures the most, and so on and so on. So we expect it to be in descending order. Cool? Awesome. I know I'm talking fast or a lot, but great. So after we add up the variance, so right here, so this first number is the variance captured by PC1. This is captured by PC2, 3, 4, 5, up to 6. We add them all up, we get 82.59% of variance of the data is captured after applying PCA, which is what we expected because that's what we told our PCA function to do. We told it at least capture 80%. If we get rid of principal component 6, then we have to subtract 7.45, which is below 80%, which is not what we asked for. Just a little, I guess, more information on how that happened. Great. So now we could go back to the matrix. We could go back to the hedge fund firm that decided to hire us for whatever reason and wanted to hire students. And now we could tell a little bit more about the scatter plot that we have. So the first things first, as I said before, the clustering. Most of the stocks fall into the same cluster, which we could safely assume that they kind of behave the same. Okay, so that's one thing. Another thing is some sectors, because I'm just going to stop moving my mouse. If you guys look where it says color equal, I don't know why it says color. I Googled as much as I can. I couldn't figure out how to change the color, but you can see where it says color equals. It says the symbol, and then it says the sector that company's in. And if we pay attention really closely, the few stocks that are away from this cluster, the sector they're in, they're the same sectors over and over again. So the financial sector, we have technology, basic materials, those sectors. I'm going to zoom in for you, Professor. I forgot to zoom back in, sorry. Okay, great. Okay, where are we? Oh, okay. So like I was saying, like the financial sector, energy sector, because we have 2 energy stocks here, financial technology, those sectors don't seem to be as clustered to each other compared to the other sectors. To make it even more, services, the sector services, the stocks in services, they all seem to be clustered in one place. So we could kind of safely assume that if a stock in the services sector goes up, maybe the other stocks in the service sector will go up as well, right? There's also utilities. I know it's hiding right here somewhere, right there. Utilities, we won't find utilities out here alone at any of they're all the same ones. Technology, that's a linear. Healthcare, technology. So sectors like utilities and services, we can assume that the stocks in those sectors behave the same. One last thing we could say from this graph is that specific stocks like INTL and technology seems to always be away from the cluster, away from majority of the stocks in the market. Because here INTL is chilling on its own, INTL is by itself, it's alone over here, by itself over here. So that also gives us the confidence to say that, you know what, if the market, majority of the market seems to be doing bad, or at least the 293 stocks that we're looking at is doing bad, we can't automatically assume that INTL is also going to do bad as well, because it seems like its behaviors don't match the other stocks in the data. So that's what we could tell the hedge fund firm. Hopefully they like us enough to not fire us. So that's PCA, and that's the first part of our job, seeing the similarity behaviors between the different stocks. Now we could actually get into what I think is fun, the machine learning part. So just to describe what machine learning is very quickly for people who have never heard of it, it's really essentially just taking large amounts of data and training a machine to have better educated guesses and predictions. It's obviously a huge field and there's so much more to it, but I can't get into that. And a quick example is everyone here has an email and we all have a junk folder. And some of you might wonder, I don't know if anyone thought of how it works, but the junk folder automatically, the junk email gets sent to it. So that's actually machine learning. So what your email does is that it looks at the emails that are already in your junk folder and maybe any emails that you manually push to the junk folder, and it learns how it looks. It sees what address sent you the email, the subject title, the stuff in the email. It kind of reads it. So if it constantly sees emails and the subject line is, congratulations, you won $50 billion, call me to claim your prize, that's obviously scam. And so every time you get an email like that, your email knows this is scam. I'm gonna by myself put it in the junk without you telling me to. So that's machine learning, I guess. It is. It's just a very simple example. So in our case, we wanna use the data that we have to predict the prices of the stocks, because that's what we're working with. I'm gonna apply the machine learning model. I'm gonna use a linear regression. It's just the simplest type of model starters could work with. It's just a straight line that best fits our data, and it uses it to kind of make predictions on the stocks, really put in a very simple way. We're gonna apply it twice. The first time we're gonna apply it to our data after we applied PCA to it. So to the data that has only 6 dimensions, and we're gonna track how long it takes to train the model and also see the performance of the model. After that, we're gonna apply it to the original 12 dimensions, and we're gonna see how long it took to train that and see the performance of that model. Okay, it's easy, quick code. We're actually almost done. The point is, we are expecting the model that's being trained with only 6 dimensions after applying PCA to be quicker than the model that we're applying only the original data with the 12 dimensions. But the accuracy, this is the trade-off point, the accuracy of the model is gonna decrease with the model that is using PCA after we use PCA, because there's some loss of information from the data compared to the model that we're using the full 12 dimensions should perform a little bit better, even though it's a little bit slower to train. So let me just show you. Here, we're applying linear regression. We're fitting, that means we're training the model and we're timing it. So right here, this model, after on the data that we used PCA, so the 6 dimensions, it took us 0.0059. I don't think this is seconds, so we're just gonna say time. That's how much it took us. For the model that we used, we didn't use PCA, so it's only the full 12 dimensions. When we trained it, it took us 0.0061. So it's a little difference, right? But it did take us longer to train. Keep in mind that 293 rows or stocks is nothing compared in the real world. There's thousands of data. There's even millions. I think Google might have billions of data that you use to do data analysis and stuff like that. So for us, it takes less than a second, less than half a second or whatever that is. But in real life, it could take days, right? It took weeks, months to train a model. And this little time difference goes a long way because it saves money, it saves time, resource for big companies when they're just, trying to save on resources. Anyone would. So for the prediction, let me just show you the table. So we train our model. We told our model, like, this is the price of a stock that looks like this. And now we're trying to train it. Each row is a price for a stock. So for the first row, the actual price of the stock is $12.90. Our model predicted $10.02. Not bad. It's not terrible. It's not perfect. It's not bad. The second stock, it's actually priced at $25. Our model predicted $24. Also very close. So it seems like a decent model. But if you look closer in the data, there are some times where it's just really off. Like the price of this stock is $57. Our model predicted $84, which is really off. There's the actual price of this stock is $16. Our model predicted negative. I'm not sure how it did that because we didn't really optimize the model. We didn't work or put any emphasis on the model because this is not a presentation for machine learning. But the point is, this is basically just the error, how bad the model is. The mean absolute error is like 7.4. Mean squared error is like 493. Root mean squared is 22, right? Compared to the model that we use more dimensions, even though it took us longer, our errors are a lot less. The mean absolute error is 1.7, mean squared error is 45, not 493, and the root mean square error is 6.7. So this clearly illustrates that if you use PCA, it does make your training your model faster because you're using less dimensions when you're applying to a machine learning problem. But if you're using your original data without applying PCA, there's just more columns, more dimensions to train your model with. It makes it more accurate because there's more information to learn, but it does make it a bit slower because it needs more time to learn the more data or the more dimensions. I hope my point got across well. That's it for the presentation. The 2 points I want you guys to really understand is PCA is used to reduce dimensionality. It doesn't have to be applied to machine learning. This is just one way, and I just wanted to test it out, that you could apply it to machine learning, but it's used for data analysis and all that sorts of stuff. And the second thing is, if you do apply it to machine learning, data science type of problems, there is a trade-off between speed and accuracy because PCA reduces dimensionality, which kind of just in its nature, you're going to lose some information. So it does make your model a bit weaker. So the accuracy might not be as strong. Yeah. Thank you. That is it. That is all.